Have you ever dreamed of walking on the lunar surface and encountering mountains taller than Mount Everest? Or stepping onto terrain formed by one of the largest impacts in solar system history? Today, we embark on a journey to uncover the geological mysteries hidden within our cosmic companion, the Moon, and discover how its story is intrinsically linked to Earth's own history. The Moon we see every night harbors a dramatic tale of cosmic violence and remarkable geological transformations. When we gaze up at its silvery face, we're looking at a natural museum of the solar system's early days. Each crater, mountain range, and dark plain, what we call lunar seas or maria, tells a chapter of an epic story that began over 4.5 billion years ago. These features aren't just random marks on our satellite's surface. They're carefully preserved evidence of ancient catastrophes and massive geological processes that shaped both the Moon and Earth. The lunar seas, despite never having contained actual water, are vast basaltic plains created by ancient volcanic eruptions. The countless craters, ranging from microscopic pits to enormous basins hundreds of kilometers wide, serve as a record of impacts that bombarded our cosmic neighborhood during its tumultuous youth. The Moon's surface is like a time capsule, preserving a record that has long since been erased on Earth by weather, erosion, and plate tectonics. Without an atmosphere or significant geological activity, the lunar surface has remained largely unchanged for billions of years, making it an invaluable archive of our solar system's violent past. When we study the Moon's geology, we're not just learning about our satellite, we're uncovering clues about Earth's own history, the origins of life, and the fundamental processes that shaped our cosmic neighborhood. The story written in the Moon's rocks and craters continues to inspire scientists and dreamers alike, pushing us to explore further and understand more about our place in the cosmos. If you're fascinated by cosmic mysteries like these, make sure to subscribe to our channel and hit the notification bell. Join us as we continue our exploration of the universe, one celestial body at a time. Our next stop will take us deep into the Moon's geological wonders, where we'll uncover even more surprising secrets about our faithful cosmic companion. Let's journey back to a time roughly 4.5 billion years ago, when our solar system was young and chaotic. The story of the Moon's formation begins with one of the most dramatic events in Earth's history, a celestial collision of unprecedented scale that would forever change our planet and create our faithful cosmic companion. Picture our young Earth, still forming and cooling, when suddenly a Mars-sized object called Theia came hurtling through space on a collision course. This wasn't just any cosmic impact, it was an event so massive that it literally ripped a piece of our planet apart. To help visualize this incredible moment, imagine two scoops of ice cream colliding in slow motion. Just as one scoop would partially merge with the other while sending droplets flying outward, this cosmic collision caused part of both Earth and Theia to merge, while other portions were violently ejected into space. The impact was so powerful that it heated both bodies to extraordinary temperatures, turning solid rock into molten material. The energy released was unimaginable, enough to partially vaporize both bodies and send a spectacular plume of superheated rock and debris spiraling into orbit around Earth. Scientists estimate that the temperature at the impact site might have reached up to 10,000 degrees Celsius, hot enough to vaporize most known materials. This ejected material didn't just disappear into space. Instead, it formed a magnificent ring around our planet, similar to but far more massive than Saturn's rings today. Over time, gravity began its patient work. The debris within this ring started to cool and clump together, with smaller pieces gradually joining larger ones. This process, known as accretion, continued for perhaps as little as a few months to a few years, remarkably fast in geological terms. The material that didn't fall back to Earth eventually coalesced into what we now know as the Moon. This explains why the Moon's composition is so similar to Earth's mantle. They both contain pieces of the same original bodies. It also explains why the Moon's orbit is gradually moving away from Earth, as it has been since its formation. This giant impact hypothesis, or Big Splash theory, is currently the most widely accepted explanation for the Moon's formation. It elegantly accounts for many of the Moon's unique characteristics. Its size relative to Earth, unusually large for a satellite, its lack of a large iron core, much of the heavy elements remained with Earth, and the similarity in isotope compositions between Earth and lunar rocks. The evidence for this dramatic origin story comes from multiple sources. Moon rocks brought back by Apollo missions show a remarkable similarity to Earth's mantle rocks in terms of oxygen isotopes, suggesting a common origin. Computer simulations of the impact match what we observe in the Earth-Moon system today. Even the Moon's current orbital characteristics can be traced back to this violent beginning. Understanding this cosmic collision helps us appreciate not just how the Moon formed, but how such impacts shaped our entire solar system. The Moon's birth story reminds us that our cosmic neighborhood was once a far more violent place, where collisions between planet-sized bodies could literally create new worlds. And perhaps most importantly, it shows us how our Moon and Earth have been linked since the very beginning, truly cosmic siblings born from the same catastrophic event. The formation of the Moon would go on to influence Earth in countless ways, from the rhythm of our tides to the stability of our planet's axis, making it an essential player in the story of life on Earth. But that's another fascinating chapter in this cosmic tale that we'll explore soon. Picture the Moon in its infancy, a world so different from the cold, silent satellite we know today. In those early days, following the colossal impact that created it, the Moon was a hellish sphere of molten rock, a true magma ocean that wrapped around its entire surface. This vast sea of liquid rock reached temperatures that would make even the hottest places on Earth seem cool in comparison. As this primordial Moon began to cool, an extraordinary process called geological differentiation took place. Much like how oil separates from water in a glass, the various minerals and elements in the magma ocean began to sort themselves according to their density. The heavier elements, primarily iron and nickel, slowly sank through the liquid rock toward the Moon's center, eventually forming its metallic core. This process was gradual but relentless, driven by the inexorable force of gravity. Meanwhile, lighter minerals and elements, particularly those rich in aluminum and calcium, rose to the surface like foam on a wave. These materials would eventually solidify to form the Moon's primary crust, the very surface we see today when we look up at the night sky. This ancient lunar crust, much of which still survives, is composed largely of a light-colored rock called anorthosite, giving the Moon its characteristic pale appearance. Take a moment to envision this incredible scene. A world so hot that rocks flowed like water, where the surface glowed with an intense orange-red light, radiating heat into the cold vacuum of space. The temperature was so extreme that even materials we consider utterly solid on Earth existed in a liquid state. This molten world would have been an awe-inspiring sight from Earth, appearing far brighter and larger in the sky than the Moon we see today. The cooling and crystallization of this global magma ocean wasn't a swift process. It likely took millions of years. As the surface began to solidify, a fascinating phenomenon occurred. Dense minerals that had crystallized would sink back into the still molten depths, while lighter ones continued to float upward, creating complex patterns of circulation within the cooling magma. This process helped to establish the basic structure of the Moon we know today, with its layered interior of core, mantle, and crust. The remnants of this dramatic period in lunar history are still visible today. When Apollo astronauts brought back samples from the Moon's highlands, they found abundant anorthosite, the light-colored rock that formed as the original crust of the magma ocean. These rocks, some of the oldest ever found in our solar system, provide tangible evidence of the Moon's molten past and help us understand the processes that shaped our celestial companion. This ancient magma ocean did more than just sort the Moon's materials. It set the stage for all subsequent lunar geology. The thickness and composition of the crust it created would influence where later volcanic activity would occur, where impact craters would form, and ultimately shape the face of the Moon that has fascinated humanity for countless generations. Understanding this early chapter in lunar history is crucial to comprehending not just the Moon's evolution, but also similar processes that occurred on Earth and other rocky planets in our solar system. When early astronomers first gazed at the Moon through primitive telescopes, they noticed large dark patches on its surface. These mysterious regions appeared smooth and dark against the lighter, more rugged terrain surrounding them, reminiscent of seas on Earth when viewed from a great distance. Thus, they named these features Maria, singular mare, the Latin word for seas. Though we now know these areas never contained water, the poetic name has endured through centuries of lunar exploration. These dark patches, visible even to the naked eye from Earth, tell a remarkable story of violence and volcanic activity in the Moon's past. Each lunar mare began its existence as a massive impact basin, created when enormous asteroids or comets slammed into the Moon's surface billions of years ago. These impacts were catastrophic events, powerful enough to crack the moon's crust and trigger volcanic eruptions on a scale that's difficult to imagine. The formation of a lunar mare followed a dramatic sequence of events. First, a massive impact would create a huge basin, sometimes spanning hundreds of kilometers across. The impact's tremendous energy would fracture the lunar crust deep into the mantle. Then, like blood welling up from a wound, dark basaltic lava would rise through these cracks and gradually fill the basin. This process wasn't quick. The flooding could continue for millions of years, laying down multiple layers of lava flows. The composition of these maria reveals their volcanic origin. They are primarily made of basalt, a dark volcanic rock rich in iron and magnesium. This basaltic composition explains their darker appearance compared to the surrounding lunar highlands. When Apollo astronauts visited these regions, they found the mare basalts to be similar to volcanic rocks on Earth, though with subtle but important differences that reflect the unique conditions under which they formed on the moon. The largest of these features, Mare Imbrium, Sea of Rains, spans over 1,100 kilometers across, a testament to the incredible scale of the impact that created its basin. Another notable mare is Mare Tranquillitatis, Sea of Tranquility, famous as the landing site of Apollo 11 and humanity's first steps on another world. Each mare has its own character and history, with variations in age, composition, and formation processes that scientists are still working to understand fully. Perhaps most fascinating is what these maria tell us about the moon's thermal evolution. The fact that the last major mare formed about 2.5 billion years ago suggests that the moon's interior has since cooled significantly, ending the era of large-scale volcanism. This cooling history helps us understand not just the moon's evolution, but also provides insights into how smaller planetary bodies develop over time. Today, we can see these ancient lava plains clearly during every full moon. Their dark surfaces create the familiar pattern of the man in the moon, a face that has watched over humanity throughout our history. These seas of stone, though never touched by water, have ironically helped nurture humanity's dreams of sailing across the cosmic ocean. The study of lunar maria continues to yield surprises. Recent missions have revealed that some maria contain higher concentrations of titanium than others, suggesting variations in the moon's internal composition. Scientists have also discovered that the margins of some maria hide vast networks of underground lava tubes, which could potentially serve as natural shelters for future lunar bases. What geological feature of the moon sparks your curiosity the most? Is it the vast dark maria, the towering mountains, or perhaps the countless impact craters? Share your thoughts in the comments below. Let's explore your theories and observations about these fascinating lunar landscapes together. When we think of mountains on Earth, the mighty Everest or the majestic Alps might come to mind. However, the lunar mountains tell an even more dramatic story of cosmic impacts and geological forces that dwarf their terrestrial cousins. Among these lunar giants, the Montes Apenninus stands as one of the most spectacular mountain ranges in our solar system, stretching across more than 600 kilometers of the lunar surface. The Montes Apenninus, named after Earth's Apennine Mountains in Italy, forms part of the rim of the enormous Mare Imbrium impact basin. These mountains rise abruptly from the dark Mare Plains, with peaks soaring to heights of over 5,000 meters. Unlike Earth's mountains, which typically form through the slow collision of tectonic plates or volcanic activity, these lunar titans were born in an instant, created by one of the most violent impacts in the moon's history. The formation of lunar mountain ranges differs dramatically from their earthly counterparts. When massive asteroids struck the young moon, they didn't just create craters, they literally pushed and compressed the lunar crust, forcing it upward and outward in massive rings around the impact sites. This process created what we call impact rims, which include some of the most impressive mountain ranges on the moon. These mountains are essentially the remains of the moon's crust, twisted and thrust upward by unimaginable forces. But perhaps the most astounding feature of lunar mountains is their sheer scale. While Mount Everest reaches an impressive 8,848 meters above sea level, it's dwarfed by the moon's highest peak. Mons Huygens, the tallest mountain on the moon, soars to approximately 5,500 meters above its surrounding plain, and when measured from its base to peak, it reaches a staggering 15,400 meters. This incredible height is possible largely due to the moon's lower gravity, which allows mountains to grow taller without collapsing under their own weight. The lunar mountains also showcase remarkable geological features unseen on Earth. Without atmospheric erosion, rain, or vegetation, these peaks remain razor-sharp and pristine, virtually unchanged since their formation billions of years ago. Their slopes are covered in ancient lunar dust and dotted with impact craters, creating an otherworldly landscape that would seem alien to any mountain climber from Earth. The lunar mountains also tell us about the moon's geological history. By studying their composition and structure, scientists have learned that many of these ranges are composed of anorthosite, a light-colored rock that formed during the moon's early magma ocean phase. This composition differs from the darker basaltic rocks found in the Maria, providing crucial evidence about the moon's early development. These mountains played a crucial role in lunar exploration history as well. During the Apollo missions, particularly Apollo 15, astronauts explored the foothills of the Apennines, collecting samples that helped reveal the moon's violent past. The dramatic terrain near these mountains also provided some of the most spectacular photographs ever taken on the lunar surface. From a future exploration perspective, lunar mountains hold special significance. Their peaks include areas of eternal light, spots that receive almost continuous sunlight due to the moon's low axial tilt. These locations could prove invaluable for future lunar bases, providing consistent solar power. Additionally, the deep valleys between mountain ranges often contain areas of permanent shadow, where scientists believe water ice might exist, a crucial resource for future lunar settlements. The stark beauty of lunar mountains serves as a reminder of the incredible forces that shaped our solar system. Standing at the base of Mons Huygens, an astronaut would need to look up at an angle nearly twice as steep as one gazing up at Mount Everest from its base camp. These mountains stand as silent sentinels, preserving the evidence of cosmic catastrophes that occurred billions of years ago, waiting for future explorers to unlock more of their secrets. The moon's surface is a masterpiece of impact craters, ranging from microscopic pits to enormous basins hundreds of kilometers wide. Unlike Earth, where weather and geological activity constantly reshape the landscape, the moon preserves its impact scars with remarkable fidelity, creating a pristine record of our solar system's violent history that spans billions of years. The extraordinary preservation of lunar craters is primarily due to the moon's lack of an atmosphere and active geology. On Earth, rain, wind, ice, and vegetation quickly begin to erase impact craters. Plate tectonics eventually destroy even the largest impact structures. But on the moon, once a crater forms, it remains virtually unchanged. There's no wind to blow sediment, no rain to cause erosion, no plants to take root and break down rocks, and no atmospheric chemicals to weather the surface. The only significant changes come from subsequent impacts or the occasional moonquake. This perfect preservation allows scientists to use craters as a natural dating tool, employing a method called crater counting. The principle is straightforward but powerful. Older surfaces have accumulated more craters than younger ones. By counting the number and size of craters in a particular area, scientists can determine the relative age of different lunar regions. This technique has been refined by correlating crater densities with absolute dates obtained from moon rocks brought back by Apollo missions. Among the moon's countless craters, Tycho stands as one of the most fascinating and well-studied examples. Located in the moon's southern highlands, this relatively young impact crater is a spectacular sight even from Earth. Created approximately 108 million years ago, practically yesterday in geological terms, Tycho spans about 85 kilometers in diameter and plunges 4.8 kilometers deep. Tycho's most striking feature is its system of bright rays, long streaks of ejected material that stretch across the lunar surface for hundreds of kilometers. These rays are visible during a full moon even to the naked eye, appearing as bright lines radiating outward from the crater like spokes on a wheel. The rays remain bright because they're young enough that space weathering hasn't had time to darken them, providing another clever way for scientists to determine the crater's relative age. The crater's formation was a catastrophic event. The impacting asteroid, estimated to have been about 8 kilometers wide, struck the moon at speeds exceeding 15 kilometers per second. The impact released energy equivalent to millions of nuclear weapons, instantly vaporizing rock and sending debris flying across the lunar surface. This debris formed Tycho's characteristic rays and also created the crater's terraced walls and central peak, a mountain that rose from the crater floor as the surface rebounded from the tremendous impact. Tycho's central peak, rising about 2 kilometers above the crater floor, provides valuable insights into the moon's composition. The impact was so powerful that it brought up material from deep beneath the surface, allowing scientists to study rocks that would otherwise be inaccessible. Similar processes occurred in other complex craters across the Moon, effectively turning impact sites into natural drill holes into the lunar crust. The study of lunar craters has revealed fascinating details about impact mechanics. Scientists have identified different types of craters based on their size and morphology. Simple craters, like those we might make by dropping pebbles into sand, have smooth bowl shapes. Larger impacts create complex craters with central peaks, terraced walls, and ejecta patterns. The very largest impacts formed multi-ring basins, many of which later filled with lava to become the lunar Maria. These impact scars also tell us about the history of our entire solar system. The density and distribution of craters across the Moon's surface provide evidence for the late heavy bombardment, a period about 4 billion years ago when the inner solar system experienced an intense surge in impact events. This knowledge helps us understand not just lunar history, but the development of all terrestrial planets, including Earth. Modern spacecraft continue to discover new aspects of lunar craters. Recent missions have revealed that some crater floors contain deposits of ice, preserved in permanent shadow where temperatures never rise above -150 degrees Celsius. These ice deposits, potentially valuable resources for future lunar missions, demonstrate how the Moon's craters continue to surprise us even after centuries of observation. The Moon's craters, these ancient scars of cosmic violence, serve as both a record of our solar system's tumultuous past and a laboratory for understanding impact processes throughout the universe. Each crater tells its own story, preserved in the unchanging lunar landscape, waiting for future generations of scientists to uncover its secrets. The relationship between Earth and its Moon extends far beyond mere gravitational attraction. Their connection has profoundly shaped our planet's evolution and continues to influence life on Earth in remarkable ways. Let's explore this fascinating cosmic partnership and its implications for our past, present, and future. The Moon's geological influence on Earth manifests most visibly through tides. As the Moon orbits our planet, its gravitational pull creates a bulge in Earth's oceans, causing them to rise and fall in a predictable rhythm. This tidal force doesn't just affect our oceans, it also influences Earth's crust, causing it to flex and move in subtle ways. This phenomenon, known as tidal friction, has gradually slowed Earth's rotation over billions of years, lengthening our days from an initial 6-hour period to our current 24-hour cycle. The role of tides in life's evolution cannot be overstated. The regular ebb and flow of tidal waters created unique environments along ancient coastlines, where life likely took some of its first steps from sea to land. These tidal zones served as natural laboratories where organisms developed adaptations to survive both in and out of water. The rhythmic nature of tides also influenced the development of biological cycles in countless species, from the spawning patterns of marine creatures to the feeding behaviors of coastal birds. Lunar rocks have become invaluable time capsules that reveal secrets about Earth's distant past. When Apollo astronauts brought back samples from the Moon, scientists made a remarkable discovery. Many lunar rocks contained isotopes identical to those found on Earth, but different from other solar system bodies. This evidence strongly supported the giant impact theory, suggesting that the Moon formed from debris ejected when a Mars-sized object collided with early Earth. These rocks also preserved information about the solar system's early bombardment period, helping us understand the similar challenges Earth faced during its formative years. The Moon's stabilizing effect on Earth's axial tilt has been crucial for life's development. Without the Moon's gravitational influence, Earth's axis would wobble chaotically, causing extreme and unpredictable climate variations that could have made complex life's evolution much more challenging. The steady rhythm of seasons we experience today is largely thanks to our lunar companion's steadfast presence. Looking toward the future, the Moon holds immense importance for space exploration. It represents humanity's first step into the cosmic ocean, serving as a potential staging ground for deeper space missions. The Moon's geological resources could prove invaluable for future space endeavors. Helium-3, abundant in lunar soil, could fuel future fusion reactors. Water ice, detected in permanently shadowed craters, could be split into hydrogen and oxygen for rocket fuel and life support systems. The Moon's reduced gravity and lack of atmosphere make it an ideal location for astronomical observatories and research facilities. Its far side, perpetually shielded from Earth's radio noise, could host sensitive radio telescopes capable of peering deeper into the cosmos than ever before. The extreme environments found on the Moon also provide unique opportunities to test new technologies and materials under space conditions. The geological processes we observe on the Moon help us better understand similar phenomena on Earth. Studying lunar volcanism provides insights into Earth's own volcanic history, while impact craters on the Moon help us comprehend the threats posed by asteroids and comets. This knowledge is crucial for developing planetary defense strategies and understanding Earth's geological evolution. The Moon also serves as a natural laboratory for studying space weathering and radiation effects, critical knowledge for designing future space habitats and protection systems. Its surface preserves a record of solar activity spanning billions of years, helping us understand long-term patterns in our star's behavior and its potential impacts on Earth's climate and technology. As we continue to explore and understand the Earth-Moon relationship, we're constantly discovering new ways in which these two celestial bodies are interconnected. From the ancient tides that shaped life's evolution to the future possibilities of lunar bases and interplanetary travel, the Moon remains an integral part of humanity's story. Our satellite's geological history, preserved in its rocks and craters, continues to provide invaluable insights into our own world's past and crucial knowledge for our species' future among the stars. As we conclude our journey through lunar geology, we find ourselves in awe of this remarkable celestial body that has captivated humanity since the dawn of consciousness. The Moon stands as far more than Earth's faithful companion. It serves as a pristine geological museum, preserving the dramatic history of our solar system's earliest days in extraordinary detail. Each feature on the lunar surface tells a compelling story. The vast Maria, those dark seas of ancient lava, whisper tales of tremendous volcanic forces that once shaped our satellite. The towering mountains, some reaching heights that dwarf Earth's greatest peaks, stand as monuments to catastrophic impacts that occurred billions of years ago. The countless craters, from microscopic pits to enormous basins, document a violent period of solar system history that would otherwise be lost to time. What makes the Moon particularly special is its role as a time capsule. Unlike Earth, where weather, erosion, and plate tectonics constantly remake the surface, the Moon's features remain virtually unchanged since their formation. This preservation allows us to study processes and events that occurred billions of years ago as if they happened yesterday. The lunar surface is, in essence, a perfectly preserved snapshot of our solar system's turbulent youth. The Moon's geology also provides crucial insights into Earth's own history. The rocks brought back by Apollo astronauts have revolutionized our understanding of both worlds' origins and evolution. These samples continue to yield new discoveries, demonstrating that even after decades of study, the Moon hasn't revealed all its secrets. Beyond its scientific value, the Moon serves as humanity's gateway to the cosmos. As we look toward a future of space exploration, our satellite offers both a testing ground for new technologies and a potential stepping stone to deeper space. The geological resources preserved in its rocks and craters may well become the foundation for humanity's first permanent presence beyond Earth. The story written in the Moon's geology reminds us of our place in the cosmic dance. It shows us that Earth and Moon are not merely neighbors in space, but partners in a profound geological narrative that spans billions of years. From the catastrophic impact that created the Moon to the ongoing gravitational ballet that drives Earth's tides, these two worlds remain inextricably linked. As we end this exploration of lunar geology, we're reminded that science is an endless journey of discovery. Each answer we find leads to new questions. Each discovery opens new horizons to explore. The Moon, despite being Earth's closest celestial neighbor, still holds countless mysteries waiting to be unraveled by future generations of scientists and explorers. If you've enjoyed this journey through lunar geology, we invite you to join us for our next exciting exploration. Hit the like button and share this video with fellow space enthusiasts who share your curiosity about the cosmos. Until then, keep your eyes on the stars and your mind open to the wonders of the universe. Don't forget to subscribe to ensure you don't miss any of our upcoming cosmic adventures. Remember, every time you look up at the Moon, you're seeing not just a bright object in the night sky, but a natural history museum that has faithfully preserved some of the most dramatic moments in our solar system's past. Stay curious, stay passionate, and keep exploring the mysteries of space with us.